Good morning, good afternoon, good evening, depending on where you're from. My name is Jay Lee from KAIST. I'm pleased to introduce the third plenary speaker of this conference, Dr. Kai Sundmacher from Max Planck Institute for Dynamics of Complex Technical Systems, Magdeburg, Germany. Professor Kai Sundmacher got his diploma studies in chemical and process engineering at the Clausthal University of Technology in 1990, and his doctoral degree of engineering from the same university in 1995. And from 1995 to 1998, he was working as a research leader. 97-98, he was a research fellow at the University of Newcastle in the UK, and he was awarded, okay, let me pronounce this right, habilitation and Venia Legendi in the subjects of chemical and separation engineering. And Dr. Sundmacher won numerous awards, including Carl Zerbe Award by German Scientific Society of Petrochemistry in 1998, Arnold Eucken Award by German Society of Chemical Engineers in 1999, and Maya Stuckmann Award by Corpus University of Technology in 2008. And he has been a professor for process systems engineering at the Otto von Guercke University, Magdeburg, since 1999, and the director of the Max Planck Institute for Dynamics of Complex Technical Systems, Magdeburg, since 2001. He's also the executive editor of Chemical Engineering Science at Elsevier and has an Einstein professorship at the Chinese Academy of Sciences. And since 2010, he has been a guest professor at East China University of Science and Technology in Shanghai, China. Now, today, his presentation is entitled Multiscale Design of Process Systems for Efficient Chemicals Production and Energy Conversion. Please join me in welcoming Dr. Sundmacher.
Thank you very much, Professor Lee, for your very kind introduction. Ladies and gentlemen, good morning. Welcome to my lecture dedicated to the multi-level design of process systems for chemicals production and energy conversion. I would like to thank the organizer, in particular Professor Ghani, for his very kind invitation to come here and for an excellent organization of a fantastic conference here in Copenhagen. I think we all agree that chemical engineering, and PSE as part of chemical engineering, has to serve the needs of society, and we see really big challenges in the near future in terms of productivity, for example, where we have to supply water, food, fuels, healthcare products for 10 billion people in the middle of the century on this planet. And we also agree, I guess, that we have to create sustainable processes. Sustainability is also a big issue on this conference. We see it in many contributions these days, that we have to rely on solar, wind, and energy and biomass primarily. And at the same time, the expectation is that the functionality of products like batteries, colors, etc., should be improved even further, and new functionalities have to be implemented into the products. We will also see a diversification of products, much larger variety when it comes, for example, to personalized medicine, APIs. It's clear that we have to generate many compounds, very specific molecules, tailor-made molecules, so to say. That is another challenge. Furthermore, on-demand production and flexible factories, also factories which can cope with fluctuating energies, is another big challenge for process systems engineering. And at the end of the day, of course, the expectation of the society is that we can all do this and derive technologies to allow them to live at a high standard of living at low costs and lowest environmental impact. That is the expectation, and it's clear that we can meet these expectations only if we are able to derive a next generation of chemical and energy processes. I would call them green processes because some of them should have features which we do not see in today's technologies and processes in industry. So highly productive, selective, based on renewable feedstocks and energies, of course. We have to close the global cycles, in particular the carbon cycle, and also other cycles like the phosphorus cycle. Also phosphor, we are running out of phosphor, as you may know, in 70 years. We have another problem with other resources. And of course, the processes at the same time have to be inherently safe and cheap. Now, when in the past we have relied very, very much, and this is still true for many industrial companies, on classical design of flow sheets for chemical processes. We have raw materials which are pre-processed. They run into a reactor or reactor system, whatever. Then it comes to the separation system. And at the end of the day, we need some recycles, and we isolate products and separate them from side products. And we have relied very much, conceptually speaking, on the unit operations concept. The unit operations concept is now 100 years old. Maybe you know that in 1915, in this Arthur D. Little report, the unit operations concept was mentioned for the first time. So the question is, should we have a big party on 100 years unit operations? Well, it was very influential. It was a very influential concept, and it's still a very important basis when it comes to also optimization of processes, because we have ready unit operations, we have models for them, we can play with that and try to make superstructures based on those unit operations and try to squeeze out the best configuration. In many cases, people rely on established devices, so we have, so to say, libraries with ready technologies, and we can put that together, and then we have a whole plant or so. That is nice. On the other hand, we have seen during the last 20, 30 years process intensification actions. Here I have a very popular example for you, the Eastman-Kodak process for methyl acetate production, and I think it's still a kind of killer application of process intensification actions, because as we see here, we have, we have here instead of a network of one reactor followed by 10 separation devices, primarily distillation, extraction, and decantation, we have only one single column inside which the reaction is performed simultaneously with the distillative separation. And due to the special features of that particular reaction system, esterification reaction, it was possible to extract methyl acetate and water, so the products of this reaction as pure products from that single column. That is, of course, very, very good example how we can replace a network of unit operations by one highly integrated process. On the other hand, we also have seen many innovations based on chemical tricks. Playing with the molecules is another important field where we can search for process intensification options. Here I have one example for you, the Basile process. Biphasic acid scavenging utilizing ionic liquids. It is a synthesis of an alkoxyphenylphosphine, where you normally use a tertiary amine as an acid scavenger, and then you run into a solid liquid slurry at the end of the day, because your products are partly in the solid phase. And that is, of course, not so beneficial for process operation. Instead, if you use this ionic liquid as the acid scavenger, then you generate a product mixture which is purely in the liquid-liquid phase and much easier to process. And in addition, this is a side effect, this side product autocatalytically activates the reaction itself. And due to this phase changing, changes of the phases, we can, or the BASF at that time was able to move that process from a batch reactor to a very smart jet-type continuous reactor with a space-time yield increase by a factor of 8 times 10 to the power of 4, which is a very impressive example how chemistry and changing the molecules can have a big impact on the process operation. And there are many more, as we all know, process intensification options in our toolbox of today. This is from this Millennium issue of CEP, the famous paper of Stankiewicz and Moulin, where they have listed up all the equipment and methods available at that time in process intensification. Since that, we have now found more possibilities also to systematically screen that. And many of us are working on process intensification, and also on this conference we see many nice examples how we can revolutionize partly our processes by using some of these tools in the box. So in other words, we are still moving from the unit operation concept, and I would call this a paradigm shift actually in chemical engineering, also in process systems engineering. Unit operation concept was very influential. It is based on existing devices, ready solutions, but it often imposes constraints for breakthroughs in productivity, selectivity, and flexibility, etc. It narrows, so to say, the solution space for process design and optimization. And that was the motivation in my group some years ago to start the development of a new concept, which we call elementary process function concept, which is thinking in terms of elementary functions to be fulfilled on the different scales of the process system, and to design an optimal process route in an abstract way from educt to product, and thereby consider the whole spectrum of possibilities in terms of mechanisms for mass transfer, heat transfer, or so forth, which are provided by physics, chemistry, and also by biology. Maybe in the future we may use some of the synthetic biology approaches also to improve our biotechnology processes in particular. So this paradigmatic shift and our developments led us to thinking in terms of this pyramid or this hierarchy. Our process hierarchy is structured in 4 levels. When you decompose, so you analyze your process, normally you have an existing plant. This is the top level, the plant level, and you analyze that means you decompose that into still process units, which are available there. And in the units, phases are interacting. So in our philosophy, different phases form situations for process on the process unit level. So the mass transfer, the heat transfer between these phases, it has to be considered on that red level. And underneath there is a molecular level, which is very important for the phase level, because as we all know, the phases are ensembles of molecules. And so we have also to consider this molecular level, because that offers some very interesting options for new decision variables, so to say. And these days we have seen in the molecular systems engineering sessions how that can have a big impact on the overall performance of a chemical production process, for example. So after point 1, beyond unit operations, I now come to the second point in my lecture here, the multi-level design approach, and I would like to illustrate that along an example which we have considered in the last few years, namely the synthesis of linear aldehydes from longer chain alkenes, olefins, which can be obtained or harvested from renewable resources. And I would actually run through these different levels, starting with the molecular level, because in designing the system, we should start with the molecules first and then move on to the phase level, process unit level, and the plant level. This is our philosophy. And after this example, I would like to show you also how we can transfer the same way of thinking to energy processes, with 2 examples for you, with the power-to-gas technology and a fuel cell vehicle technology. And finally, I will conclude the talk with some final remarks. So let's start with the molecular level. On the molecular level, we have a number of main decisions to make. Normally, your target product is, of course, fixed, the green one. Question is, how can we make this target product out of certain molecules? And the stoichiometry says that certain combinations of A and B will make this product C. So this is just the stoichiometry of the main reaction, which is the main platform for your process design. And of course, the question is always, do we have coupled products or side products? So what kind of byproducts do we have? And so once we have fixed A and B, the other question is, do we have really catalysts in order to enable these reactions to really proceed, to really happen? And do we need solvents for the catalysts or any of these products in order to stay in certain phases? And once the molecules are fixed, once the main mass fluxes are determined, then of course we can also determine the heat which has to be supplied or removed from the process and the power. The main decision criteria here should be atomic efficiency. So the number of excess atoms should be as low as possible, and you can see many examples in existing technologies which violate, so to say, the atomic efficiency criterion. When you check that, you see that there's much space still for optimization also of traditional chemical processes, because many of them have too many, so to say, excess atoms in their reactants. Transformation efficiency is with regard to the number of intermediate steps. So how many steps do we have really to go through in order to make our target product? The feedstocks for A and B, okay, they should be available, of course. The price is an issue, the storage is an issue, maybe also the safety. Sustainability. The CO2 footprint can be also directly derived from a very simple flow scheme on this molecular level. And we can also discuss catalysts here. Are there catalysts available? Normally, this is not something which process engineers are developing. They have to interact with industrial chemists, technical chemistry, in order to find really a catalyst with an acceptable price, activity, selectivity, longevity, and separability. Also, separability is an issue which I will touch in the remainder of my talk in a few slides. And last but not least, another class of auxiliary players, so to say, on this level are solvents. Also, they have to be considered in terms of price, hazardousness, availability. So if we apply this now to the example which I have promised to you, the formation of a long chain aldehyde, namely tridecanase with a C13 linear aldehyde, which is depicted over here. It's a biodegradable compound, by the way. It can be used as a flavor, plasticizer, and as a surfactant. And you can easily derive that this molecular structure, of course, is very close to 1-dodecene, which is a corresponding C12 alkene. And by addition of hydrogen and CO, this is just an addition reaction without any coupled byproduct, which is very good in terms of atomic efficiency. You can directly make this tridecanal. But when you perform this reaction, it's also automatically clear that the functionalization of this double bond sitting here can be never done such that you harvest 100% of your desired target product. Instead, you have also other aldehydes, primarily the branched aldehydes like this one here, the 2-methyl-dodecanal, which is a non-biodegradable compound. You still can sell it at the market, but at a considerably lower price, but it is not biodegradable and, so to say, not green at this point. The other point is that once you have fixed now this molecule is nice, but you have to go to other molecules in order to ask yourself, so what is really the supply chain in order to make this molecule? Well, 1-dodecene can be made from 1-dodecane, which can be isolated from crude oil. And via thermocatalytic dehydrogenation, you can make this molecule very easily. The Evonik company recently launched a project, Plenary, or it's more or less finished now, but there they have investigated the photocatalytic dehydrogenation, having in mind that maybe some renewable energy can be used for functionalization of this 1-dodecane. But still, the 1-dodecane comes from crude oil. A more attractive route, which is a more green one and a bio route, I would say, is route 2, where we might take ethanol from biomass, so bioethanol, And via dehydration, you can get bioethylene. And this bioethylene is now very popular, for example, in Brazil. And via the shell higher olefin process, via addition some hydrogen, you can, so to say, oligomerize the ethylene and make longer chain alkenes like a 1-dodecene. So there are now interesting routes, and I would say there's an option to make really this molecule, the biodegradable molecule, also from bioresources. So from that perspective, this route is good. So in the remainder of my talk, I now focus on the hydroformylation part of this process, and we should ask ourselves, how can we make the best hydroformylation process of that process chain? First, you have to isolate, of course, or identify a catalyst. There are quite a few catalysts, namely transition metal compounds. Rhodium is the most active transition metal in this series. It's 1,000 times more active than cobalt, for example, and many processes are still running on cobalt in hydroformylation industries. The other ones are not really relevant. But also the price is more than 1,000 times higher than for cobalt. So if we use this catalyst and rely on the high activity of rhodium as a central atom of our catalyst, then it's absolutely clear now that quantitative catalyst recycling is necessary for economic process operation. Activity is one part of this molecular catalyst. The other part is a chelating ligand. And here is just a cartoon of many ligands, and I could have you shown even more ones from chemistry books and homogeneous catalysis. This is taken from the book of my colleague Professor Beer from Dortmund University, and he has here investigated during his whole business life many homogeneous catalysts, in particular hydroformylation. And the recommendation was from batch screening experiments that this PFAS catalyst is pretty expensive. It has nearly the same price per mole as rhodium has, but it provides a high chemo and stereo selectivity with regard to the formation of this desired trigonal molecule. So in the remainder, we are talking about the PFAS catalyst in combination with rhodium. Now this, as I said, this catalyst is now very expensive, so we have to keep it in the process. It's a homogeneous catalyst. It's nice, you can design it. Unlike heterogeneous catalysts where you have a support and you never really understand the interaction between the active compounds and the support, here you have really catalysts which are designable. When I saw this first as an engineer, I was really fascinated to see that here are opportunities, future opportunities in particular, because the models are not so safe so far, for PSE approaches. So really molecular systems engineering of these molecular catalysts. Theoreticians in chemistry have already succeeded a bit to make some predictions on how these catalysts are working, but this is still very uncertain, so to say, and many questions are open. But in particular, I would like to emphasize here that this is really a catalyst which can be designed, and now we can also integrate another separation function to separate this catalyst, or catalyst function to enable this catalyst to be separated from the product mixture. Okay, the ligand has to interact with a reactant, and this catalyst has to stay in this phase, of course, but how can we separate it? One option is to create a bond, covalent bond from this ligand to a solid support. But very often you change then your activity and selectivity. This is normally not the way to go. Another option is to keep it as a homogeneous catalyst and to bind to this ligand a polymer chain, where you can now design the length of this polymer chain. And if you make this very long under certain conditions and lower temperatures, you form a solid phase, and you can precipitate your catalyst and filter it out of the process after the reaction, which is one option. Filtration is also, and dissolution again of this solid catalyst is not so nice. Another possibility is to keep it in the liquid phase and to keep this polymer chain so long that it is the catalyst as such, the whole configuration is always in the liquid phase, but can be kept back by membranes like organophilic nanofiltration membranes, or if it is even larger, this molecule, by ultrafiltration membranes. This is another possibility. Of course, the reactants, they have to be separated from this, and in other words, we need in organophilic nanofiltration, in our case, the aldehydes being formed have to be separated via this membrane, and only the catalyst should be kept back. Recent investigations also in Dortmund in the group of Professor Gorak have shown that this is a nice technology, and also in other groups, Cole Hamilton, for example, in the UK, they have investigated that for a long time, the ultrafiltration and nanofiltration membranes, but there are still many problems, pore blocking, etc., limited selectivity, and so forth. Another option, which is much simpler, I would say, than the design of a membrane, is to offer, so to say, a second phase into which only the reactants are jumping because they have a much higher affinity to this phase than the ligand, which would like to stay in phase one. So that brings us to the concept of solvents in order to separate this catalyst. So how can we design a solvent in order to run into a biphasic regime after the reaction? And that is shown over here. We have here shown the strategy for catalyst separation. You see here a triangle of two solvent compounds, namely a polar one and a non-polar one. And the reactant, so our olefin, should have an intermediate polarity between these two extremes. And during the reaction, we would like to stay here, somewhere here, where here is a binodal curve, so here is phase splitting, but the operating point is selected such that during the reaction we have a homogeneous liquid phase. Now, by phase of a temperature change, maybe by cooling down, we can, with a clever selection of these compounds and the right polarity sequence, so to say, we can generate conditions such that under separation conditions, so after the reaction at lower temperature, with the binodal curve is here, and now our post-reaction mixture is sitting here, and now we are discussing this triangle with the product, so with the tridiagonal. We would like now to separate this, and according to this tie line, we have two different product phases, namely the phase where our target product is inside, and the other phase, which should be here the more polar one, where the catalyst would be sitting in case that we have a ligand, like bifephos, which also has a high polarity. So it likes to stay in that phase. So that is the idea. And the people in Dortmund, Professor Beer, they call it thermomorphic multi-component solvents. So instead of designing with CAMD methods or so a particular new solvent molecule, the philosophy is here to make use of existing solvent molecules and try to find conditions and mixtures under which this TMS behavior happens, and such that we can easily use the temperature, an easily accessible process variable, in order to separate the catalyst after the reaction. The state of the art in selecting those solvent compounds is they do it based on experiments, LLE experiments, and Hansen parameters as descriptors, so to say. The challenge is, from our point of view now, to incorporate also the molecular catalyst structure, because so far, when selecting these solvents, people, the chemists, do not normally look at the catalyst. They just look at the product and how the product can be harvested from the mixture. But due to the very high impact of catalyst loss on the overall process performance with regard to the catalyst cost by catalyst leaching, we have really to incorporate here the molecular structure in selecting when selecting the solvents for this TMS system. And the way how we did it was we were making use of the COSMO model, so the conductor-like screening model, which is a quantum chemical approach and is depicted here in a, I must admit, a very busy slide, but I will try to guide you quickly through. So we start with defining this catalyst ligand structure, and we perform via turbomole a DFT calculation in order to find a stable configuration, the most stable configuration of that molecule. And via Cosmo, you can then calculate the screening charge density surface. And that is then the input information which you can directly use based on statistical thermodynamics to make predictions, for example, on chemical potentials, and also to make predictions then based on that on the relative solubilities of or solubility of this catalyst ligand in different solvents. We did the same also for the product molecule, the tridecanal, in order to find out what are the best solvents for the catalyst and for the tridecanal. We had a number out of a database which is provided by Cosmologics and their Cosmo RS software. We had directly access to nearly 8,000 solvent species, out of which we selected about 400 product solvents and 100 catalyst solvents, which have high or low solubilities for the respective molecules. That leads us to, in this binary pair of the two solvents, to 40,000 options to make a TMS system, but only a few of them really show this TMS behavior in a reasonable temperature window. So we can make predictions now in which temperature window those solvents show the requested behavior, that they are monophasic under reaction conditions and biphasic under separation conditions, so room temperature or even lower. And out of these many combinations which led to TMS behavior, we could also take out quite a few which were not environmentally friendly or due to their hazardousness are not, of course, solvents which we should really take. In the next step, then, we teamed up with Professor Geer's group in Dortmund in order to also make experiments in order to check whether the predictions based on this Cosmo model are correct, or which of the candidates which we have squeezed out can do a good job for this process. And here are the results. I've shown you here a number of binary pairs, TMS systems, for practical reasons, and because Professor Beer has had done a lot of experiments already with N-decane. One of these solvents was fixed, while the other one, the polar one, was varied. And what we see here is in blue the catalyst distribution coefficient, which in this plot should be as high as possible, and the distribution coefficient or partition coefficient for tridecanal, which should be as low as possible. And we checked that in experiments. So we did some LLEs and measurements, and also some reaction engineer measurements, because we have to make sure that these solvents not only are the right solvents in order to make this separation, but also solvents which allow the catalyst really to do the job. And here are the experimental results. So based on this pre-selection, let's focus here on this partition coefficients of the ligand, so the phosphine ligand, and the rhodium itself, the central atom, so to say. What we see is that 3 remaining candidates are here: dimethyl formamide with N-decane, NND methyl acetamide, and the NMP. So they have nearly the same performance in terms of the separation of this catalyst. But with regard to the selectivity of this catalyst in the reaction, dimethyl formamide, DMF, combined with N-decane seems to be the best option. And so that prediction was made. Fortunately, I would say, we found out that this system was also the system which was used over many years by Professor Beer. So, and he has developed this over the years based on his know-how as a chemist and empirical data harvesting, so to say. But here, the system is confirmed to be, out of a large set of potential candidates, really the best option for this particular task. So once you have now isolated the catalyst or identified the catalyst and a suitable separation technology, so to say, system, the next step is now to really understand the catalytic reaction cycle and other byproducts, because we all know that it is not possible to design really an industrial process only based on the reactants of the main stoichiometric reaction or one-side reaction. We have to understand the reaction and the catalytic cycles, and you see that this is really complex. And my colleague Andreas Reiter-Morgenstern in Magdeburg with his reaction engineering group have worked out this catalytic cycle. They have found out that there's a catalytic activation step, then we have in blue hydroformylation cycle, and in as side reactions we see hydrogenation steps and isomerization steps. That was all squeezed out with enormous efforts using analytical tools or advanced analytical tools like Raman, ER, and IR, and so forth. And at the end of the day, they were possible, together with the Wozny group in Berlin, to reduce that network and to boil it down to 5 main reactions and 7 main species. And what we see here is that there's an isomerization reaction of this one alkene. This is the desired reaction R1, the desired product. But as a matter of fact, all the time we lose some alkene due to the hydrogenation and we form alkanes. We have a reversible isomerization due to the moving of the double bond along this molecule. And as a consequence of the same, we also form some isoaldehydes, so the branched aldehydes, which we do not want. So the challenge is now later on the phase level to influence the system such that we are only running into this N aldehyde and we block, so to say, the other reactions. So as these are now the molecular levels, the molecular players, which we have here collected, so to say, and with that we are now running onto the phase level. On the phase level, we are taking an abstract view, namely, instead of looking at a reactor, a specific device, we consider a meta-element, generalized meta-element, here characterized by a state vector x of t, temperature, pressure, velocity, chemical composition, and that is manipulated, that state, by fluxes, internal and external fluxes, namely mass fluxes, the reactions inside, stress, so when it comes to forces and we move it through the process, also the mechanical forces have to be considered as in this generalized flux vector, the heat flux and also the work. And then we can track this meta-element along a route in the state space, and the task is now to steer this meta-element from a starting point to a final point and to find something like an ideal process route just based on the reaction kinetics first. So we consider only this meta-element. This is not linked directly to any device, to any particular process unit. We try to find, so to say, the ideal travel route of this Lagrangian observer, if you want. The travel route direction can be derived easily from the balance equations of the meta-element. Here it is given and it's depicted again here. Namely, at any point along this process route, you can span a vector diagram which indicates elementary route directions, as we call them. They can be identified as the column vectors of a matrix which consists of the capacity matrix inverse multiplied by a flux coupling matrix where our stoichiometry and other factors are sitting. And the main point is now that the length of these vectors, so the intensity of the fluxes, mass and heat fluxes, decides about the route direction x dot. The attainable region can be here also depicted at any actual point from here. And of course, you have also some boundaries here of this, the dashed lines, due to equilibrium conditions where the fluxes are vanishing due to thermodynamic equilibria. So this concept was a basis to set up a dynamic optimization problem, which is written down here in a standard way, but in the variables which I've just introduced. We have a cost functional, we have the balance equations in the form of ODEs, and we have also some algebraic equations, namely thermodynamic state equations and the reaction kinetics, and maybe some inequality constraints due to bounds of temperature, pressure, conversion, if you want. The main point is now that we touch directly the external fluxes as control variables. So we use them, and we use them as unconstrained control variables in our dynamic optimization problem in the very first step. But this only can be solved then at the end of the day if we have really information about the reaction kinetics, about the reaction rate expressions. So together with the Seidel-Morgenstern group in Magdeburg, we did a number of iterations in order to identify the reaction kinetics for that particular system. And the best way we found for this system was to do perturbation experiments in a semi-batch reactor in order to parameterize this reduced reaction network. The perturbation was done by actions on alkene input and syngas composition and amount. And we were also able to change the temperature via the heat flux. And by doing this and by application of standard optimal experimental design techniques, here the D-optimality criterion was chosen, we were able to parameterize the reaction rate expressions. And you see that we have nonlinear equations, of course, as function of temperature and the concentration measures in that system. And based on this information, we were then able to solve this dynamic optimization problem for a given or fixed conversion of the one alkene. So for any specific conversion, we get here now one optimal control action along this process route, which gives you the best selectivity. So this is the best selectivity line for any conversion you decide to have for this one alkene. And it contradicts the textbooks. For simple reactions, normally what we get is a decreasing line of the selectivity over conversion, but the surprise here was to see, due to this highly nonlinear reaction network, that we have obviously a branch at very high conversion where we can achieve high selectivity and high conversion at the same time. And that was also confirmed experimentally in the semi-batch reactor experiments, by the way. And here you see the fluxes which belong to this point. We have to dose hydrogen and carbon monoxide. And the optimizer says that no dosing of alkene is necessary. Only the syngas compounds have to be dosed in stoichiometric ratio. So that was a prediction. And if you want to understand, of course, we try to get an insight. Why is it so? And the surprising effect here was, it was not surprising because we had understood this reaction network, or if you have this reaction network really clarified, then you can see that what happens is that in the first phase of this batch reactor or semi-batch reactor, you have primarily the hydroformylation reaction to the desired product, but unfortunately also some loss due to the isomerization reaction. But then after some time, when a certain level of these internal alkenes have been formed, you can reverse this reaction. And by a backward isomerization, you can form even more N-aldehyde. So this trick requires relatively long residence time in the reactor. Nevertheless, by doing so, you can achieve an increase again of the selectivity at relatively high conversion. And that was not so intuitive. It was not predicted by the chemical partners in our research network at that time. Okay, but now the problem is, okay, how can we really implement this ideal solution on the reactor level? So for that purpose, we have developed here my former PhD student, Andreas Peschel. He has developed in his PhD dissertation a very nice strategy, namely by moving through a three-level design procedure. We can first determine the optimal route, as I've just showed to you, with unlimited fluxes. Then we can limit the fluxes by really writing down the kinetics for mass and heat transfer. And then we have additional constraints due to limited kinetic coefficients and also limited environmental levels. For example, the cooling temperature or the heating temperature, of course, has certain bounds. And that leads to limited fluxes, and that leads to another type of control control actions. And then the third step is how we can technically approximate the decisions being made on level 2. And for that purpose, we have now two options. Either we can implement the solution which we have obtained on level 2 in a semi-batch reactor, an optimally operated semi-batch reactor, of course. But the other option is, of course, to do this in a continuous way by discrete dosing. And here we translate, so to say, the time coordinate into a residence time coordinate in space of a continuous reactor, for example, of such a segmented flow reactor with reactant dosing. Of course, you will have some loss of optimality simply due to the fact that you have only a limited number of discrete dosing points, for example. And in addition to that, you might have additional limitations due to mass transfer and so forth. You might also select another reactor rather than that, a bubble column or so, by investigation of the optimal solutions under variation of the transport coefficients. You can mimic different regimes in different apparatuses and thereby then at the end of the day select the best solution for your system. But even then, you cannot be sure that in a continuous reactor this solution really leads to the optimum in real world under real world conditions. And you have to consider residence time distribution effects, of course, because the continuous reactor will be not an ideal plug flow tubular reactor. It will have some backmixing properties. And the way how we deal with that is we introduced here probabilistic input. Namely, we considered a distributed resonance time. For example, here the distribution function is given. And then we propagate this, so to say, through our reactor model or our fluid element model, if you want. And thereby we project it into the criterion space. For here, example, if we take again the selectivity, then we can get now a Pareto set of the mean selectivity, which you get here, and also of the variance of the selectivity of the meta-elements moving through your reactor with a non-ideal residence time distribution. And then each point along this Pareto set, of course, corresponds to one specific design. The good point is that for this particular example, we found that we can really robustify the reactor design by the control actions such that the reactor is nearly insensitive to the residence time effects, which is a very interesting result here. Okay, let me come now finally to the plant level. On the plant level, we have now to consider also the separation part. So far, I only talked about a standalone reactor. What about the separation? We have recyclers. We can consider first an ideal selective separation, which is able to isolate all compounds of the reaction system, that is the assumption, at very pure quality. And then you can again play with the fluxes as control variables with the external fluxes. And the only change now in our dynamic optimization problem is that we have recycle constraints according to this mixing point here at the entrance point of the reactor. And the surprising thing is that the selectivity diagram now shows much higher selectivity for the recycle system rather than for the standalone reactor. And now we get a curve which corresponds to what we see in many textbooks, a decreasing selectivity with increasing conversion. But again, we have a small local optimum at high conversion here. Here we see the control actions. Dosing of syngas and dosing and 1-alkene is now recommended by ConOpt, the optimizer which we have used here for solving this dynamic optimization problem. And if we now look into the concentration profiles and the temperature and pressure profiles of the system, we see again that that here obviously the isomerization plays a very big role due to this recycling. Now we can recycle back the isomers and can consider them as reactants, so to say, in a second pass through these reactors. And we level up, so to say, in this recycle system our isomers, and thereby we can achieve much higher selectivities at the end of the day for the desired target product. And finally, we have also tried to translate this into a real-world process design, which is now this optimized reactor with, not indicated here, side dosing of alkene and the syngas compounds, followed by a flash and a decanter unit, followed by vacuum distillation for organic solvent separation and for the separation of the N and isoaldehyde compounds for a given capacity and purity. And we have here then optimized the real production costs. We have taken cost models. We have modeled, by the way, these unit operations with standard models, with relatively simple models. Nevertheless, we believe that this yields relatively good predictions regarding the minimization of the production cost. I should also mention that we did a lot of efforts in order to describe the real-world multi-phase thermodynamics here in this decanter and flash system by using PC-Saft as our thermodynamic model here. Okay, and the result is given here. What you see here is a cost difference with regard to the optimal point. The optimal point is our optimal reactor embedded into this recycle structure, which I've just showed to you. We see again, it is recommended to go for a very high conversion, much higher than a CSTR, stir tank reactor, should be operated at. And you see that we can squeeze out, so to say, 2.8% savings compared to the CSTR solution related to the overall cost of the total flow scheme. But that might translate with a given capacity into some $million per annum. And here again, we see that this minimum of the cost was only achievable by a very sophisticated dosing of the syngas compounds. And we were surprised to see that with the cost function as objective function, the optimizer here decided not to go for alkene dosing, only to dose separately hydrogen and CO. The reason for that was that there was a penalty function in terms of costs for dosing equipment, because for this dosing, of course, requires additional equipment that might lead to a higher investment cost of your reactor, and that is why the 1-alkene dosing was not actively used. Okay, I think my time has run out. I should stop here. I just show you quickly, if you give me 2 minutes, yeah, thank you for that, that we have also used the same philosophy, actually, regarding the methods. There's nothing really new. We have used that also successfully for a number of energy processes, chemical energy conversion processes, and maybe I switch through the slides to this final system. The operation of the fuel cell car is still a big vision in the car companies because of the limited range of battery cars and the much better range of future fuel cell cars. But we know all that the problem is a hen and egg situation. We need hydrogen filling stations, but for hydrogen filling stations, we need a hydrogen distribution infrastructure and so forth. When it comes to the fuels, which you might use to make hydrogen also on board of the car, and you find that natural gas is a very attractive compromise, so to say, because we have in many countries, in particular also in Germany, we have a large infrastructure to distribute our natural gas. And nowadays already we have, I think, a 5% car fleet or so in Germany, which is running on natural gas with internal combustion engines. And that brings us back to the idea to do onboard reforming based on natural gas directly on board of the car, and to isolate then pure hydrogen for operating the PEM fuel cells. In that particular case, we were designing the reformer under using fluxes for water and oxygen. Oxygen is necessary to get rid of the byproduct carbon monoxide. And we were also trying to figure out whether there's an extraction technology to get very, very pure hydrogen. Actually, there is one, palladium membranes allow us to selectively extract at very high purity hydrogen from those mixtures. And we, and this is, I think, an important point here, a message, the kinetics for designing this process were taken from the group of Professor Maestri at Politecnico di Milano. He has, based on quantum mechanical calculations, he has developed microkinetic network for methane reforming, and based on that and some reduction techniques, which I skip here, we were able to derive a reformer concept, which is an autothermal microchannel methane reformer with more than 1,000 channels, 100 micrometer inner diameter each, equipped with palladium membrane and rhodium catalyst inside. And we have also embedded this into an overall process scheme, which we believe is an attractive option for future fuel cell cars. That brings me to really the final slide of my talk. I hope I have shown to you an interesting multi-level approach to process systems design. We call it EPF, Elementary Process Functions Methodology. The key element is the dynamic optimization of fluxes acting at matter elements and traveling through the process. That allows you to systematically compare different process intensification options. At the moment, we are also working on transferring these ideas and philosophies to particulate processes and bioprocesses. And finally, I would like to acknowledge DFG funding for our Informed Research Center, which is located in Dortmund, Berlin, and Magdeburg, where many of the research is being done around this hydroformulation example. Also, the International Max Planck Research School, our graduate school, was supporting some of the PhD students working on these topics. And I would like to thank many partners nationally and internationally. And with that, I would like to thank you very much for your very kind attention. Thank you.
Well, thank you for taking us through very comprehensive and holistic overview of this new paradigm of process development, a very intensified talk. I think we are running behind, but nevertheless, we should take some questions at the cost of your lunchtime, of course.
So, François Maréchal from EPFL in Lausanne. Thank you for your talk and really inspiring. I'm not sure that I did understand what was the objective function that you are using in the when you define the trajectory. Yeah. The objective function. So what do you minimize? You said it was a cost function.
We did it on the phase level. We were only considering not costs, but technological objective functions. In that case, the selectivity with regard to the desired target product, the aldehyde. But later on, when moving through the process unit and so through the hierarchy towards the plant level, we moved over to a cost function. So finally, the whole process flow scheme with this sophisticated dosing